electric car.
I resume. All right. That is the third and the final lecture by Kong, who is going to tell us about other details of the EIC and perspective from this panel point of view. The floor is yours.
Thank you. Okay, lecture 3. So I will talk about a little bit of what I left yesterday. I didn't finish. So remember the EIC, there are so many different physics, but everything is centered around this so-called QCD confinement. And then there are 3 pillars, or 4, depending on how you categorize them. So you have imaging, trying to look at the fundamental structure of protons, nuclei. And then you also have this puzzles with the nuclear mass and spin, right? Remember, the mass is kind of dynamically generated with interaction in the vacuum. And then the spin, of course, you have quarks, you have gluons, you have orbital angular momentum, and collectively they contributed to the spin. So finally, there's this last scientific mission, which is the gluon saturation. And if you think about, just 5 years ago or 6 years ago, there were 2 options of where to build the electron-ion collider. I know many of you are actually from Jefferson Lab community, right? So one of the advantage as a Brookhaven is that we are on a higher energy frontier and we are colliders, right? We have this experience. And then one of the most compelling support for this building this high energy electron-ion collider is to look at the gluon saturation. So the gluon saturation, so remember I have this cartoon that in DIS, there are 2 independent variables, right? So X and Q squared. So Q squared is this kind of spatial resolution, and X is this time resolution. That going from low to high energies, you're essentially going to lower X. You slow down the proton, or you accelerate the proton, you slow down their time. So the time dilation kicks in, you start to see more and more gluons. So I posed this question, I planted the seed in your mind yesterday, is that when does this gluon stop? Because by very simple arguments, we call it the unitary bound, is that cross-sections, when you have fundamental cross-sections, particle collides, this cross-section has to be finite. So there's an apparent paradox is that you have to have a finite cross-section. And then the density is related to your cross-section. So density cannot be infinite growing. Right? So that the idea is very intuitive that there are things that just cannot be infinite. So how does this actually work? Which is a beautiful idea. So we actually had this discussion, informal discussion last night. So now I want to draw my proton very big. Well, it doesn't matter if it's a proton nucleus, same. And you have this photon comes in. And as Alexa draw this picture yesterday, is that this is defined by your photon resolution. So the length scale here is, we call it, is 1 over Q. Okay? Remember, Q squared is just minus Q. So this defines basically your resolution, the spatial resolution, your scale. So think about as a transverse plane. This is, you can do an area which is 1 over Q squared or R squared, which is the area that your photon is probing. So the analogy I would say is that you can have a chopsticks, or you can have a big hammer or whatever. Right? It depends on the probe, the size of your probe. So this is the size of the probe is defined by the Q squared or the Q, and you define your area. So now this thing starts to evolve when you start to do the evolution in energies. Because if you look at this area right now, you can have this one. So let me bring it here. So in the so-called in high X or in lower energies, you only have a few photons inside of the probe area. Okay? And then as you go to higher and higher energies, call it 1 over x, it becomes much more dense. Okay? This is exactly the picture I draw yesterday, right? The more that you go in energies, the more time dilation it is, and then the gluon starts splitting. Okay? You get more and more gluons to show up in your probe. So basically your probe, you fix your probe and you let it go into higher and higher energy. So then you can think about it as the gluon starts to show up in this area and it just keep increasing. And then until when does it stop? So one thing that worth mentioning here is that because this is in quantum mechanics, you actually have uncertainty principles to govern that the positions, the length scales, and the momentum scales is basically bounded by uncertainty principles. So what does that mean? Is that when you decide the probe, the property of your probe, the size of your probe, you decide, basically constrain the typical momentum and position scale, the length scale and the momentum scale. They are conjugate variables. So now if you go into the very high energies, you're essentially, if you keep the same size of your probe, going to higher energies, you start to have more gluons to show. Right? This is exactly what I talked about. So then if you really think about intuitively, is that this is the regime where the gluon starts to split. Okay, 1 gluon becomes 2 gluon. And you can have more splitting. The rate of this splitting is just happening more until, very naively, gluon can self-interact, right? In this regime, there's no space the gluon can go. They have to be packed on top of each other, right? They start overlapping. So this is what we call the recombination. This process starts to kick in. The gluon starts to merge. Because like, let's say in the classroom right now, we have this many people. We can have a few people. We can have a lot more people. At some point, we're going to be shoulder to shoulder because there's no space to go. We all get squeezed into such an area. And this area is defined by your probe. So this probe is very important. So to put it more quantitative, this is called a linear regime. And where this linear comes from is because the gluon starts to split, all right? So we can write it very simply. Let's say this depends on x because the energy and the probe, the size of your probe. The rate of change as a function of energies goes basically, you have some alpha s, some constant, and then linearly with basically you can think of it as a number of photons or actually is a scattering amplitude. Okay? So the idea is that in this regime, this linear, you decide your probe size, and then as you go into higher and higher energies or lower x, the splitting happens as linear because every gluon can split into 2. So you have n gluons and individually can split into 2. Okay? So then when you go into very, very high energies, right, this gluon starts to really pack to each other and they start to merge or recombine. So now this nonlinear regime is the same thing. So I this way. I have the same thing here. And this is with a minus sign because gluon splitting is to add number and then gluon merging is to subtract number, right? This is intuitive. So now let me ask you, why is it nonlinear? Why is it quadratic? Anybody? This is actually, in our field, every day we will mention this word, QCD, non-linear QCD evolution, non-linear QCD dynamics, non-linear gluon dynamics, non-linear blah, blah, blah. All of this means almost the same thing, right? This is the term. This is the nonlinear part. Now, I'm asking you, why is this nonlinear? Here I go.
Is it n choose 2?
Yeah, exactly. Right? So because now you can have one gluon split into two, when they recombine in a confined area, you need to pick your partner, right? You have many different options to pick. But splitting, you can only split into two. But then when you have to find a partner to merge, you have to pick. You have different options. So this actually goes quadratically. And that's exactly why this is nonlinear. And then when these two things is, battle as you go into a higher energy, and eventually gluon saturation means when these two terms are balanced. So the rate of growth and the rate of recombining becomes equal. And that is where saturation comes. So in other words, if you wanted to study the small x dynamics or nonlinear dynamics, it doesn't have to be always reach the saturation, the point, right? So this point is something that we don't know. We wanted to reach to a higher energy and higher densities to get there. But a lot of the experimental observable trying to be sensitive to this nonlinear term. So if you think about this, you can also think about in terms of position space. You can also think about this as in the Fourier transformation, which is in the momentum space, right? So as I said, these are basically related. You define your scale. You basically define your length scale, area scale, or your momentum scale. So now if you translated this or transform this to your gluon momentum distribution, which is now is KT, which is the momentum transfer momentum in the transverse plane. And then you can also draw similar diagram or relations, right? You just have to do the Fourier transformation. And actually this looks like this, okay? It's a dropping, this is 0. So here, when you have the high KT, this is the regime where it's very, we call it dilute, which is at the lower end, lower part, okay? So when you're starting to basically evolve this, you can actually getting into the regime is more and more dense, right? They're equivalent. So by a given probe, you evolve the X, you're basically moving into this regime. And then at some point, because the recombinations, this gluons actually starts to drop. So now there's an intuitive way to think about this, is that when you have this, the size that is defined, now you're going to lower and lower X or higher and higher energies. So now let's think about this. The total momentum is fixed, right? So now you wanted to distribute this same momentum into many, many partons, right? At the beginning is 3 partons, 5 partons of gluons, 10 gluons, 50 gluons, 100 gluons. So what does the momentum change for each gluon? It becomes smaller, right? So this is a natural intuition that when you go into more and more dense regime or the gluon starts to show up, it naturally splits this distribution or this momentum. But then when you into this nonlinear regime, when the gluon starts to recombine, right? Think about this gluon, the 2 gluon has smaller momentum. When they recombine, they got a little bit more momentum. So the momentum actually increased. So this is just another way of saying that when you're in this recombination regime, the momentum scale actually get pushed higher on average. So think about we have 100 gluons. Each one of them has 1% of momentum. And then when you combine into 50, everybody gain effective 2. Of course, it's not effective 2. I'm just trying to build a picture. And then you recombine more, everybody get faster, right? They get more momentum because they start to merge. So there's a balance between a lot of gluons. So because they have to merge, so eventually there's a natural position where this is actually peak. So this part doesn't exist, right? It doesn't exist. In principle, if there's a uncontrolled growth, this will go all the way shooting to infinity, which is not allowed. So then the gluon densities, this is the gluon densities as a function of their momentum will start to drop. So here we call it the QS. Okay, it's called the saturation scale. And this is the most important scale for saturation physics. It's the typical momentum where the saturation sets in. And now I hope you can understand what this QS means. The QS means that at this momentum, basically this gluon distribution is the most of the gluons is at this momentum scale, because you can have splitting with lower momentum, but at some point they have to merge. So there's a balance. So when this balance happens, this is the momentum scale that you're looking at, the so-called QS. So naturally, you would think the QS depends on what? First of all, it should be 1 over x, right? There's some factor here. Because the higher the energy or the lower the x, the QS should be pushing higher. Because if this plot gets evolved in different snapshots in x, then this peak position will start to move left and right. Okay. And then another way to actually make this QS higher or changing is by changing from proton to nucleus. I think this is very intuitive because you have one proton, and then you squeeze hundreds or 200s of protons and neutrons into the same transverse area. You artificially increase the densities of the particle. So this will also make this packing going faster when you evolve in energies or in x. So then this QS, the typical momentum, will shift from left up. And then so now you ask the question, why do we care? Why do we want a denser regime? Because when you have a denser regime, it's easier to see this gluon saturation. So there's another key point here is that if you wanted to do experimentally or calculations about saturation, you wanted to have a balance. Okay, the balance is the following. So the best of the this balance is basically you want to have your probe is sandwiched between these two things. First of all, you want it to be away from the lambda QCD because lambda QCD, is very non-perturbative. That's the scale set by the QCD. A lot of this calculation cannot be carried, right? You don't want to be in that very blurry regime. Then you also want it to be in the saturation regime. In the saturation regime means that you're in this regime, right? You're in here where you can actually be sensitive. You have a lot of this saturation nonlinear dynamics existing instead of we call it the dilute regime. This is the dilute. This is the dense. So you want to be below QS, but above lambda QC. So ideally, you wanted to have this for any measurement that related to the gluon saturation. Okay, so let me give you an example. So this looks like if you wanted to, let's say, bike from New York to California. Okay, in the ideal case is that you don't want to carry, let's say, 10 tons of stuff, all your stuff. Then your bike will be not movable. It's really, really slow. Right? So that's like in lambda QCD. It's very, very slow. It's very heavy. Or you don't want it to fly, or the bike is if it goes really fast, you're not gonna see anything on your road trip, right? You miss all the fun, the natures, the national parks. So what you want is to just right between them. So you're not so heavy, but you also have a finite speed going through the country. You can see the center. So this is exactly what we want to do in saturation physics. We want it to be away from the lambda QCD. We also want it to be within the saturation. So the quantitative question is that how far is lambda QCD and the QS, right? If they are very close, then you're doomed. There's no regime you can actually do your saturation physics. If QS is 200 MeV, there's no way you can do it. It's non-perturbative. But then if this guy is as far away to the right, to the higher Q square, then you have a legit finite room, a range that you can probe your physics with this relation. And that is why we have this QS. That is, you need to use a nucleus or nuclei at high energies. You wanted to push this QS as large as possible, right? Then you can probably find a probe to be sandwiched between. So that is basically the way I would describe how we could do the saturation physics. This is true for experimentalists, for theorists, right? This is true for everyone. So hopefully the experimentalist can find a measurement, satisfy this, and then the calculations can. Okay. So this is the slides, the previous slide. I only prepare one slide. So now I hope that you can understand these plots once you see it in conferences or in the related to EIC or small x. You know, this is the BFKL, this linear splitting. And then this is the BK, which adds the recombinations, right? It's just the reverse. But this is linear. This is the quadratic because you need to find the partners. That's where the nonlinear comes in. And then, of course, the regime is that you have the X and Q square. And you want it to be in a saturation regime, but above the non-perturbative regime, but still in a very, hopefully the range is not so narrow when you push this QS further away. So this is the unintegrated gluon density distribution as a function of KT. As you see that naively, you will have this smaller momentum peak as you go to, the higher density go into smaller momentum because you keep splitting your gluon momentum. But actually, in reality, this will actually come down because of the recombination. So this is the so-called maximum density or the most typical momentum scale, and that is the QS. Okay. So this is the number that you have to remember. Okay, any questions?
So does it drop because they recombine?
Yeah. Right. So when they recombine, I mean, it doesn't work exactly, but mostly it's true. When you have a lot of gluons, they share momentum. Once they recombine, the momentum gets pushed up. The momentum gets pushed up. So basically, the lower one is suppressed. And then they go to higher. Only the gluons with higher momentum kind of survive. Yeah.
Yeah, so looking at your QS formula, it scales with the A. So if we use heavier nuclei, as you said, we can push the QS towards the right, towards the higher energy. I'm just thinking about if we, instead of, if we use a fixed target, where we have a thicker target and you have more, instead of, I'm just trying to think about, is it better to do this kind of search in fixed target than collider?
So physics is, of course, does not care whether you do fixed target or collider, right? As long as you can collide. But what matters is X. So in fixed target, generally, you cannot reach as lower X as in collider, right? So for example, electron-ion collider energy is much higher than Jefferson lab. And then, of course, if you can build like TeV muon beams and you can fix target on something, maybe you can reach the same level of X. I think that's possible. And then the other control is your nucleus number. So we can do heavy nuclei, which is you can do uranium. This is the heaviest that we run at RIC. And there's not that much room. You can push the A higher, right? So this is per nucleus. This is the densities.
How did you come up with 1/3 factor? Is it empirical?
Right. So this is kind of, think about this is the length scale, right? You see the length scale. So A is a atomic number. And then you think about this as a volume and you divide it by 3, it's 1/3. It's kind of sets this length scales of the size. And of course, the X 1/3 is because of the density is growing. It's if you do the Hera data in the PDF, it actually behaves like a power law. And that is almost like 1. So you combine these two and then make it easy, simple. It's A/X to the That's sort of the empirical numbers. Okay. All right, so the EIC. No. So this is the electron-ion collider. As I said, I will be very brief and quick. I think Christoph actually talks about the machines. So one thing I wanted to emphasize is that why do we need polarized? So this is the first electron-ion collider, obviously. We can have a very wide range of energies. Why do we need a wide range of energy? Because we want to study high X and low X dynamics, right? So we can also accelerate from deuterium to uranium. Why do we need different species? Also related to saturation, you want a different A factor. Okay. So there's a many level arm that you can play in the electron-ion collider. And then the third point is that it's the first polarized electron-proton or light-ion collider. Why do we need polarization? So this is from yesterday, because only through the polarization of the beam, we can figure out the parton spin, right? The spin-dependent structure function. And this is very clever experiments that very simple, but actually enabled by this technology of these polarizations of beam. So you need polarized electron, polarized proton to figure out this structure function of spin-dependent structure function. And then, of course, that we're capable with two interaction region. Here, EPIC is sitting at IP6, is where the star detector is sitting. So, when you see the real detector, at least there will be probably roughly 10 years. So let's do a simulation. So this is the EPIC detector. And as I'm walking into the hall, you see the detector and you go into the right-hand side, that's the forward direction, where you have a lot of the beamline instrumentations. There are 4 detector system. And Bill Lee tomorrow will talk about the forward physics and instrumentations. It's related to exactly that region, right? You go into the hall, look right where the hadron is going. And then you go back, and then you go into the electron going region, and then you will see there's a luminosity monitor, there are low Q square tagger, there are a few instrumentations from the backward region. So the backward region is where the electron is going, okay? This is basically the simulation. This is done by students, graduate students at Riverside who write the software. So this is the EPIC detector. There will be dedicated sessions about PIDs, calorimetry, so I'm not going to the details. What I wanted to emphasize is that this detector is so compact. It has almost everything. As a community in the EIC, we are very ambitious. Okay, we didn't want to give up anything. We want PID everywhere. We want a calorimetry everywhere. We want tracking everywhere. So this gave us the only options is that you make it very compact. So centimeters, even millimeters matters if you look at a drawing from the engineer. So we have tracking inside. We have the hadron going, electron going. We have different PID. It's such complicated detector. So this is the EPIC collaboration. We have 26 countries, and this number I think is still growing. It's 1,100 scientists. This is a very large community. If you see the map, that we have North America, basically everywhere. So this is the distribution. I'm one of the main organizers of this EPIC collaboration meetings in January. The next one will be in Glasgow in the UK next month. I don't know, maybe many of you will go there. And then this is basically in January at Brookhaven. So this is the schedule. Did Christoph show this? No, okay, good. So this is just the schedule, just to give you guys an idea, when are you going to graduate? When are you going to find a job? This is actually related to this table. So don't worry about the CD system. It's called a critical decision. It's a jargon from DOE. But basically, is that you have different years, and you see that at some point, FY 35, you will have some collisions, right? The physics will start there. So the baseline, hopefully, is next year, and then the construction begins the year after, and then the first collision in late 2035. Okay, so it's about 10 years. That was the number. The 10 years was the number 10 years ago when I joined. So don't worry, we have time. So the goal is trying to develop this $3 billion project. It's very funny. When we're trying to sell this to the general public, we said the QCD confinement is so-called the $1 million question. It's because there's one of this Millennium Prize problem. Do you guys know this? It's the Clay Mathematics Institute come up with this 7 problems. And then one of the problems is related to the QCD confinement or the Young-Mills and mass gap. And they give you $1 million to solve it. But in order to solve that, partially, you need $3 million to build a detector to even not start it. So I don't know how they did the math as a mathematicians. So this is basically the timeline. So for the early years of the EIC, this is very exciting. We have many programs that the HERA or anywhere else did not have. So we call it the early science of the EIC. So we have different years. We have started with silver. Okay, silver apparently is very expensive now, but then it's less expensive than, for example, ruthenium, something. This is a mid-size of the nucleus. And I think Christoph talked about this orbit thing, right, in the accelerator. And the reason why we're going with silver is that you need some medium-sized ion to be safe, right, to be circulated in the center of the orbit instead of going so far away from the orbit. So then you will protect the detector. So then as it goes on, we have polarization starts to add, and then we'll have deuteron, right? I'm very interested in deuteron. I'm interested in nuclei. I'm also interested in protons, so everything. And then helium-3, okay? So this is a very diverse program that you can do almost from the Jefferson Lab physics, high X physics, to the low X physics. Low X physics, now you know what it means. It means this, right? Small X physics, saturations. So one thing to mention is that we have about 0.5 inverse femtobarn each to H1 and Zeus. I'm part of H1, by the way. So this, even for you look at the first few years of these luminosities, we already surpass the lifetime luminosity collected at HERA. So things will be precise, much more precise. Even let's say we do standard structure function measurements, F2, FL, remember F2, FL, right? The DIS. And then very soon we're going to release the early science report. I'm one of the writer, and then together with many people, and then you can read it afterwards. So in the day-to-day practice, when we talk about EIC, now we have to put on different hats. Okay, we have to make a different categories. So this is basically 3 categories. We have the inclusive DIS, and we have semi-inclusive DIS, and we have exclusive program. So the idea is that inclusive program is that you measure 1 scattered electron, and you don't need anything else. You just need 2 independent variables, x and q squared, or y and q squared. And I spent a lot of time talking about it. But I did not spend any time to talk about semi-inclusive, but the idea is very similar. You measure your x and q squared very well from the scattered electrons, and you tag one of the hadrons. So this is how Hermit's experiments figure out the spin contribution of quarks, because they can actually do semi-inclusive. They have PID, so they can tag different flavors. So that is actually much more accurate to estimate the spin of the quarks. So the semi-inclusive actually has a lot of physics in it, right? So you have all the TMDs, fragmentations, and it's very complicated. There's a lot of room to learn. But this is enabled by semi-inclusive physics. And finally, exclusive physics is that you have only 1 particle in the final state, and then basically your target stays intact. And this is very interesting. I'm very interested, personally, very biased. It's because this almost goes back to what we talked about in lecture 1, right? It's elastic scattering. You kind of tickle your target without breaking it. And you wanted to see, for example, the form factor, right? The charge distribution or the gluon distribution. And then this is actually how each topic is related to each process. Okay, a lot of reading. So the must read is I call it the Bible, the EIC white paper and the yellow report. Together, there are thousands of pages. Hopefully that you will actually read it. It's good reading. So now I only have maybe 25 minutes or 20 minutes. So this is a very highly biased list of measurements, very unique. Every one of them is unique. So then I wanted to maybe give you guys an examples. If the EIC is built, you can have hundreds of different measurements. So the first one is called inclusive DIS or inclusive diffractions. And you can actually see that on the left-hand side, this is so-called the nuclear PDFs, right? So the nuclear PDFs is that there are certain regimes that we never perform DIS on nucleus. So there's a very low X regime. You can just by doing inclusive measurements, measuring just the scatter electron or just the X and Q square, that can already tell you a lot that we haven't learned. Because you can compare with the proton, and you see that this is one of the estimates that the nuclear effect, basically comparing the nucleon inside of the nucleus versus a standalone nucleon, right? So this one you can already going through with the structure function, measuring F2, measuring FL. Remember, FL is very sensitive to gluon. Right? So if you wanted to study something like gluon saturation, the first thing you can look is the FL, because you can just directly look at a structure function. So the second one is something I wanted to spend a little bit more time. We call it the day one measurements. And this is one of the golden measurements that a lot of the small x theorists claim that day one, they will discover gluon saturation. And if that happens, it's through this measurement. So this measurement sounds very complicated, okay? So there are other low X phenomena called shadowing, I'll explain later. But somehow saturation model is different from other models. And that's kind of how you're trying to distinguish. So let me walk you through what is this. So anybody knows what this means, this plot? I want to ask first. Maybe nobody. Okay. So let me try to explain this plot. So one of the discovery at Hera, of course, this is a bias, is that the most important discoveries is that they discover a type of events called rapidity gap events, aka the diffraction. So the diagram looks like this. Okay. The diagram looks like this. And the important part is that you have an electron, and you can determine your X and Q square, high Q square, low X, higher energies. And then this is, let's say, your proton or your A, is that somehow this type of events happens is that in the detector, there are a lot of particles produced, but there's a gap between this particle produced and your target. So your target stays intact. If you have a proton beam, the proton actually stays intact in the final state. And this is just very strange. If you think about this, right? I wanted to do this recap. I wrote it down. It takes too much time to write it. Elastic scattering, about 1 GeV, right? Remember in the 50s, they discovered that proton is not structureless because you wanted to tickle the proton without breaking it. Because at the time, you don't have enough probes to break it. Then later to slag, you discover the quarks because now you see the Birkin scaling. You actually destroy the proton. Everything is breaking up. So you see the quarks showing up. And then if you keep pushing the energy, somehow the proton starts to stay intact, right? So it's just counterintuitive. So then at the time, Hera was not expecting any of this because the higher the energy, it should be more easier to break it. Until they found out about this is called a diffraction. It's the diffraction, the cross-section, very easy. You just measure X and Q squared, require a gap, or you require the proton to be tagged in the detector. They found out about this ratio. It's about 13%, which is a huge number. So out of 10% or 15% of this event's total DIS, that they are coming from this diagram. They're coming from this diffraction. And the diffraction is that this is, we call it the Pomeron. It's a two gluon bound states. And then these color singlet states share the same quantum number as the vacuum. And then only in this kind of interpretation, they develop this formalism trying to understand diffraction in the low X regime. So this is actually a very powerful observables trying to see the density of the gluons. And because they are actually, the interpretation is that you're connecting to two gluon exchange. So you're naturally sensitive to. So this diffraction is at about 30%. So there's another one is that I don't have the time to go through the detail, is that if you calculate this in a scattering amplitude, so the diffractions actually goes as the scattering amplitude square, and the total goes to the linearly with the scattering amplitude. So there's a so-called Blattis limit, is where the scattering amplitude goes to 1, right? The probability goes to 1 that this ratio, diffractive over total, is 1/2. This is the regime where we call it the Blattis limit. Basically, your proton or your target becomes so opaque, become a black disk. Anything that throw at it, you scatter or you absorb. So this is the fundamental limit in diffraction that you will hit 50%. So now look at the number. At Hera, at 300 GeV square root of S, you hit 13%. The natural expectation is that if you can keep increasing this energy or keep increasing the densities of your target, right? It's QS, you eventually, that you will hopefully get closer to the black disk limit. Okay. So now this plot. So now if we can do a very smart, actually a smart experiment, is that, let me write it here. Is that this is 1/x or W or energies square root of S. Okay. This is the direction of the higher energies. And this is the black disk limit, about 1/2. You cannot go beyond that. And then so you have the diffractive over total. So if you look at a proton, the proton looks like this. You know, at the low energy, it's almost 0, right? Because we're passing this slack area, you know, this energy regime. The elastic doesn't happen anymore. Everything is inelastic. But at some point, when you keep increasing, this diffractive starts to show up. So then the proton looks like this. Because you actually have about 13% about this diffraction over total. So now apply what you just learned from gluon saturation. At the same energies, right, in this vertical axis, if I replace my proton to a heavy nucleus, and you can do this A200 to the 1/3, it's about 6. So you have a factor of 6. We call it the factor or the increased factor of QS. So then you're actually getting faster or easier to the saturation regime or to this black disk. So now the predictions. So how will be the, if you make a prediction, how will be the nucleus as a function of energy behave on this plot? Now we're getting to a little bit more details now. So this is the diffractive over total at a very low energy in DIS, not too low, but you know, DIS, you don't almost have anything. As you increase the energy, the Hera actually starts to show up with diffractive. At very high energy is about 13%, right? This is the Hera energy. So now my question is, as a function of energy, the same evolutions from proton, you change the target from proton to nucleus. Qualitatively, where would the nucleus curve go? Anybody? So naively, you would expect at the very beginning, there's no nonlinear dynamics. proton and nucleus should be just the same, right? So they should share a little bit of the same until they are not. They'll be a little higher. There will be a little bit boost because you're looking at the same X, same energy, but with the more nucleon packed into the area. So the probability of having this nonlinear dynamics is greater, right? All connecting to our saturation physics. So now this is the gold nucleus. And you take the ratio of this guy to this guy as a function of energies or as a function of so-called the mx, which is the final state. This is actually proportional to the center of mass energy between the photon and the target. So that if you take the ratio between this guy and this guy, which is a double ratio, right? This is the single ratio, this is the double ratio, and that is exactly it. Okay. I hope you understand this. This is a little, so this plot shows you that saturation model predicts as you go into, in a good region where you have enough energies, you actually, it's above one, where you have the prediction that is qualitatively different than so-called shadowing. The shadowing model, let me give it just one line, is that the shadowing model, because doesn't happen in the nucleon, because it's called a nuclear shadowing. So for the proton, nothing, let's say nothing changes. When you have the nucleus case, the diffraction actually is more destructive. They have this destructive interference. So you expect that the diffractive over total, this actually goes down. So that's why they're actually below one. Okay. So the author of this actually trying to update, I urge them old, and we even have a paper on this on ultra peripheral collisions using similar ideas. Okay. But this is day one. Okay. Number two, this is the spin asymmetries, right? I think you made the comment. Here is the wide phase space that we are going to gain. So now this is a very interesting experiment, and the author or the analyzer sitting across the hall, Win, is that there's a couple of unique aspects here. So now, if you remember, we wanted to polarize the beam, both sides, and you flip the polarization of the beam, trying to figure out how much contribution quarks and gluons contribute to the total spin of the proton. Now you can do proton, or you can do helium-3, in this case, helium-3, that you can measure the neutron. So you have 2 protons, 1 neutron, and you're doing this DIS experiment. How do you know you're hitting the neutron? You don't. The experiments before EIC, it's almost impossible to know which nucleon you actually hit. You can only try to do some, arguments to subtract, but EIC can do it very differently with so-called the tagging. So the tagging happens like, so you have a helium-3. If the DIS is hitting the neutron, I wanted to study the neutron spin-dependent structure function. So the quarks here will be aligned or anti-aligned when you polarize the beam this way, or the other way. But I don't know for sure that if I'm going to hit the neutron or the proton. So after you hit it, this will break up. So in EIC, we have a special detectors in the far forward directions. The off momentum detector, and we have Roman pot, where the proton will break up with the helium-3 will break up, and the proton will end up in one of the detectors. So if we know that in the far forward region, we see 2 protons and no neutron, then we know this event is actually happening on the neutron. So you can know for sure, event by event, which nucleon you're probing. So if you know the neutron for sure, then you can come up with the spin-dependent structure function for neutron, like G1P and G1N. So this is when you measure the G1N. This is exactly the pseudo data or the simulation studies that you can utilize the unique capability of EIC tagging the forward proton And don't worry, Bill Lee tomorrow will talk about this. Hopefully, the forward physics and thinking. This is why EIC is so unique. And look at this phase space. Yeah.
So can we not just install this detector in our currently accelerators?
Short answer is no. I think this will this is a question to Christoph, but the idea is that this needs to be in the design. You know, you actually, when you have different components in the accelerator, in this in the optics, you will change all the parameters. It's not so easy that you can just put a detector there, right? Everything is fixed. So when you say that the existing collider, for example, the LXC, they do have something like this, but it's just not as versatile as EIC. So at LXC, the Atlas and CMS, they have some 4 proton tagger, just like at Hera, but then we have something a little bit wider angle, so you can detect many different lines. So remember this, that we have G1N, A1N, A1P, and all of this, the phase space is wide open that we have never measured. Okay, I have to. So finally, diffractive vector meson. So this is towards the imaging, and it's also related to the diffraction. So now the diffraction is very different. Different by you don't have many particles in the final state. You only have one particle in the final state. Okay. So this one particle in the final state is that. Okay, let me just say it instead of drawing. So instead of having a lot of particle produced here, this is also a Pomeron, let's say, to the leading order of Pomeron exchange, and you have an intact proton. So if the target stays intact, we call it the coherent scattering. And the coherent scattering is sensitive to so-called the average parton density. And the average parton densities, so if you don't have the intact proton or the nucleus, if the target breaks up, what we call this is that this is sensitive to event by event parton density fluctuations. Okay, so you can do 2 things. You can measure the coherent or incoherent, trying to gain some different aspect of the structure of the nucleus or the proton. And you can do a spatial imaging because you can measure the momentum transfer. Then you can infer or transform to the position space and get an image of the gluon distribution instead of the nucleus. Sorry, I have to speed up a little bit, running out of time. So let me give you an example. So have this in your mind when you refer back to the slides, is that coherent or elastic is average density, and then when it breaks up, it's fluctuation. So what does that mean? Here, this is a map for Manhattan, New York City, the 5 boroughs. I used to live here, just out of the perimeter. So this is the population density, you see? You do the survey, right? How many people live here? You don't count the travelers, you just, the residents. So this is the coherent scattering, meaning that you're describing the population in New York City as an average densities. It's an average density profile. But then if you go to incoherent, when you break the proton, you're sensitive to fluctuation. So this is the fluctuation. This is the hour by hour, day by day, the traffic in New York City, right? So you see that Thursday, Friday, and the Saturday is actually pretty quiet. And this is the hour by hour fluctuation. And that is also a density of the population showing up in Manhattan. This is the 2 aspects of this scattering from exclusive diffraction vectormeson. And I think both are interesting and they're describing the 2 aspects. So only when you measure both, you have a full picture of New York City, right? What is the long-term residence and what is the day-to-day traffic looks like. There are 2 aspects. But this is the fluctuation. This is the result. So the result is that if you do this coherent scattering, it looks like this. Remember this form factor or this transformation? It has this diffractive pattern because the size of your nucleus is much larger than the proton. So if you do this Fourier transformation, it looks like this in the position space. This is one of the hardest measurements at the EIC, is to measure this diffractive pattern. And then for the incoherent, when you break up the nucleus or the proton, it almost stays flat on the scale. Does this ring a bell? When you break proton, somehow the cross-section stays constant? This is another way of looking at it. Even in the gluon regime, dominant regime, far away from the SLAC experiments, you still capture the same idea where the coherent one drops very quickly, had some frequency spectrum telling you about the distribution. Now it's not charge, right? Now it's gluon distribution. But then when you break it up, this almost looks flat. I mean, it's not flat, but it's much a milder slope, broader slope than coherent one. It actually captured the same physics. Okay? This is amazing. And actually, we're using a different paradigm, different language to describe this than the earlier ones. But somehow they share very similar things. I don't think in the literature people actually connected this. So if one of you interested in these directions, you should explore. So this is actually the status in March, okay? Just a few months ago. This is the students working with us. So this is the truth. This is the reconstructed. They used a very, very clever method to do this because this measurement was almost doomed. And we saved these measurements by going to a very different method. Yeah. Yes.
Is that Lisa Kessler?
Yeah, that's
Yeah, she's my colleague. She's in my lab at Kent State. That's cool.
Great. Then you know this. Maybe you can explain.
Oh.
So this is using the latest EPIC simulation, the new projective method. I should replace it. We just got published fully online yesterday or 2 days ago. And then you see that when you do the Fourier transformation, you see that this is the one that we're going to get, the red or orange one. And you see that from the blue is the star data from a phi production. We're constraining much better at the center of the nucleus. Looks very simple, but it's very, very challenging measure. So this is the very latest status, and that will be the end of the 3 experiments that I talked about. So finally, summary on the 3 lectures. The EIC physics. Let me remind you what I really think that the center of the question. How does the confinement, this QCD, non-perturbative QCD phenomenon, manifest itself in the structure of protons and nuclei in terms of momentum, mass, and spin? Right? So this is the central questions. And then my topic or my emphasis on these 3 lectures is trying to build a physics intuition to you. And hopefully you have to take this physics intuitions into account. And this is heavily based on your knowledge and experience, right? You don't randomly guess. It's an educated guess. And also, if you wanted to take to the next level, you have to be careful, right? Intuition cannot get you all the way to the finish line. We're doing science. Science is rigorous. You have to, details matter, but intuition matters too. So with both, I'm sure that you will succeed. Thank you. Thank you.
Let me just say, tonight we won't have the discussion, so I encourage you to ask him questions now.
There's no discussion tonight. It's coffee.
I have a simple question. So what we know about gluon saturation and what we are looking for from the EIC collision?
What's the current status of gluon saturation? So what do we know experimentally about on that?
Yeah, so from what we know, the experimental data are consistent with the gluon saturation picture. So for example, you have a measurement called dihadron correlation. I didn't talk about this. Maybe Bjorn will talk about it. Is that there are certain prediction of this correlation, and in STAR, we see this. Okay. But proving something true is very, very difficult. Proving something is not is much easier, right? So in all of this experimental data, we see very consistent pictures. For example, at the LXC and CMS, and also our STAR, the ultra-peripheral collisions, just the plot before, you calculate the cross-section, you compare with your expectation, it also follows the nonlinear QCD or saturation. So there are many consistent pictures, but that still doesn't buy you the confirmation. You need kind of a simultaneous proof from different angles, different signatures. In fact, if you think about this, it's almost impossible to turn off gluon saturation at high energy because this factor, X is there. You're sensitive to low X. So everything in principle should be subject to the impact from gluon saturation. That makes it harder because you cannot tell which one doesn't have, right? You can only know, like, compare everybody, either they all have gluon saturation or this whole thing is wrong. So this is the challenge. So you can read the dihadron correlation from STAR. It's a PA versus PP correlations. Yeah.
So in low X, do we really care about the masses of the quarks or no? Because at low X, we have so many gluons.
Mhm.
The concept of having mass, the valence quark max, doesn't make any sense.
Valence quark. No, valence quark is not in the picture anymore, right? You're not sensitive to valence.
And what about all the other masses of quarks?
The order of, in this picture, there's no quarks. Not enter in this picture. In the CGC or in the gluon saturation regime, there's no quarks. We don't even talk about it. It's not in the picture. Why? Because what you're looking at depends on the probe, right? Now you're in the regime, you basically choose your probe that's 99.9% dominated by the gluons. So the quark doesn't matter. Doesn't matter what it is. You're just basically not sensitive to quarks.
But there would be some valence quarks, right?
Yeah, there will be. But that you see, this is the why the subtlety about DIS, right? Is that what you're seeing depending on what you probe. Now, if you're probing just the low X regime, it's like when you accelerate a proton so fast, you slow down the proton, all this fluctuation comes out, and you only see basically the gluons, right? If you see the PDFs at low X, the gluon is dominated way over the valence quark. So the quarks, you can say, doesn't exist. It's just you don't probe it. You're not sensitive to any effect that the quarks is present. You have to go to higher X where you're more sensitive to the valence quarks to see the effect.
That regime, 99.9999%
It's cool.
quarks that the total will come from this splitting, not from the internal content. Doesn't mean, of course, that valence quarks are not two up and one down. They always such. But the number of quarks in principle can be very, very high. And 99.9999% will be from those splittings in that particular regime.
We'll go back to the gluon saturation.
There are many. Which one?
Just keep going. Maybe it was further towards right there. So I just want to try to understand the intuition behind this. So the alpha strong coupling constant is small. So is that because the saturation, the density, there's like deconfinement happening? Is that why it's considered small?
No, so alpha S small is a strong, it's a weakly couple.
Okay.
Right? Alpha S small, this is so-called perturbative.
Yeah, because it's so dense.
No, this is the dilute regime. This is dense. This is dilute.
I have that backwards.
So if you can think about this, is that, let's say higher energies, alpha S is small, right? The running coupling constant. Remember in QCD, the three guys got the Nobel Prize, right? So at the high energy, you're in this asymptotic free regime. The alpha S is very, very small. So then you have a few gluons. They are weakly, they don't interact, right? So, but then when you pack more gluons, you actually compensate it by the number of gluons in your problem. So now the alpha S times we call it the number of gluons, is at order 1. So this is where I didn't go into that direction. maybe I could. Is that when the saturation, when this the balance is actually the saturation sets in at the moment where the alpha S and your gluon number, let's use is order 1. That is where another way of thinking about the gluon saturation. So if it's yeah, so remember this is probably helpful. So there's another way to think about this low X gluon regime is that think about this in the broad daylight across the football field. Alexei is over there having a tiny little flashlight or laser. In the broad daylight, you're not going to see it. Especially on the side, there's all kind of light, pollution or anything. This is like the light is still there. It's like this valence quark, but in such a regime, you just can't see it. You're not sensitive to it. But then if you go into a different regime at night, everything is quiet, and having a laser, whoa, you can see kilometers. Right? So this is sort of the differences that depends on the probe, depends on the environment or the conditions, you're sensitive different. This analogy actually used in a lot of astronomy and looking at the sky. It's very similar.
Well, did you really say that was the dilute region, but that's after the saturation scales, right?
Yeah, dense is below. Remember? I erased it. The golden regime is. Remember this. This is also an important one. You want to be below QS and above lambda QCD, right? So where do you want to do a measurement? It's only here, ideally. Okay? Like doing this road trip, right? You don't want to be too fast, you don't want to be too slow. Yeah.
Measure this here. But you have to measure a hadron in the final state, or can it be fully inclusive?
You can do, okay, how you exactly measure, that depends on different process. You can do gluon saturation physics measurements in all 3 categories. You can do inclusive, right? You can do semi-inclusive or exclusive, like the last one. Right. The probe does, they have different sensitivities, but the underlying physics is exactly the same. Whether you measure 1 particle or 2 particles, as long as your probe is in this regime. Your Q probe can be determined by the scattered electron. You have a high Q square or Q square within this regime, or you can have, let's say, a heavy core. Like last night we talked about this. You set the scale, it can be also in this regime, right? So at LXC, you don't have electron. How do you study gluon saturation? You make your scale of your problem in the event. Basically, you can do it in this way as well. That's exactly the same.
Kind of spectator technology obtain the structure of free neutron because if you use a nuclei, it's bonding on free neutron.
But yeah, something. Okay, good. So, can I answer the question, Alex? Did I hear that? Okay, let me erase. Good question. So your question is, can we use the tagging method to access the free neutron structure? Right. Okay. So we do have a paper about it. This is written by Kristen Weiss, myself, and Alex Yench. So the idea is the following. We are looking at the deuteron, was about 1.8 GeV. You have proton and neutron, right? So what you can do is that this neutron is never free with the proton in the deuteron. You don't have a neutron source. So the binding energy is very small. Binding energy of deuteron is what? I mentioned this last night. Yeah, 2.2 MeV, right? So they're actually mostly back to back in the rest frame. So what we can do is that we can probe a DIS to the neutron, and then this guy flies out to the off momentum detector. We tag the proton here, so we know that this is actually neutron. But that is still not free neutron because they still have binding, they still have momentum correlations. And if you do it at a high momentum, this is called the high momentum tail or the short range correlation of JLab physics. But then you can also do it at a low momentum. So if you look at the momentum of this proton, this is the PT of the momentum. So you can actually go, you measure down to 0, where a proton is basically at rest as it is expected. And even that, they're still bounded. They're still not free neutron. So what do? So you calculate the deuteron wave function on the light cone, and you're trying to separate this. And then eventually, this is a very actually precise theory. You can determine the absolute free neutron point is somewhere in a negative PT. It's an imaginary point. It's not physical point here. So what we can do is that we can extrapolate this all the way back to this free neutron point. Intuitively, to understand this is that this is not physical, right? PT cannot be negative. So what's unphysical? The physical is that the protons and neutrons are infinitely far away as a deuteron, which doesn't exist. So when they are infinitely far away, you don't have binding, you don't have any interaction, you completely isolate neutron, so we can study the free neutron structure. So we can extrapolate this point, free neutron structure, per x q squared, all the kinematic bins, and then we can do the free neutron structure. And you can do the inclusive free neutron structure, PDF. You can, in principle, and this has not been shown before, and if you guys are interested, you can do this as a research, to do it as a GPD extraction. Right? You can do a lot of things, a free neutron, you fill in the blank. It's completely unexplored. But the EIC can enable this by tagging basically so-called spectator tag. And this is one of the experimental programs that Brookhaven that we came up. Okay.
I have a comment on that. This isn't just theoretical, this is something being done at class. It's done at 6G era, the bonus experiment, bonus 12. The data are being analyzed.
Yeah, bonus, let me comment back. Bonus can only go down to 80 MeV. It's very, very small momentum. So what you want is that at the EIC, we can go to 0. No fixed target experiment can go to 0. So basically, bonus will stop here. You know, there's some gap. EIC can measure this, and then you can extrapolate.
Okay, let's thank Frank again. See you the one.
Quick update. This evening, we will not have the discussion. We're going over to Stony, to Port Jeff for dinner, 6 o'clock. There's some notes in the WhatsApp, but if you have a car and available to drive, can you raise your hand if you want to? Okay, so look around if you want to pair up with somebody to figure out a ride. Otherwise, the best option is there's a bus for $2.25 each way. You can use an app. And if you're stuck, see one of us, we'll get you there. But 6 o'clock, downtown Port Jefferson, okay? And we'll coordinate later. Have a good lunch.
You're on the right, know your driver, okay? Just.
Another point, those experiments for tag DIS are also incredibly difficult. Much more difficult than anyone ever thought they would be.